Hey everybody, I'm here to talk about my day 5 solution to the advent of code. I had a lot of fun doing it. Wasn't able to do like a live solve of it because I didn't have time. I had to do it in piecemeal. And part of that is, if you look at my screen, you can see my initial implementation for part 2 saturated my CPU and still took 94 seconds to solve. So if you're new to how Advent of Code works, that's usually a sign that there is a better solution and you need to think about it a little bit more. And so I just had to do that in between chores, family life, all that stuff. Anyway, we'll talk about that as we get further into it. But with that, let's just get to the solution, or get to the problem and how I solved it. You're given this input, and the idea is you have these seed numbers, and they are, you want to apply mappings to them, right? Go from seed to soil, soil to fertilizer, so on and so forth, until you get to a final location. And the goal is, can you find the smallest the smallest location among the seeds, right? The way to think about it at a high level is you're going to take a number, apply these mappings, eventually get to another number, and then if you do that over all of the seeds, can you get the smallest, what is the smallest one, right? So, excuse me, there's actually not too much to part 1. Again, a lot of it was parsing. I was able to use nom to do that. So let's just kind of look at that, and we'll build, and you'll see how the mappings work, and we'll see how I applied it, right? In this time I did it kind of in a, I don't know, object-oriented approach, but the idea is I'm going to parse an almanac. That's what they called this whole input. I'm going to parse an almanac, and I'm going to say, what is the answer to part 1? What is the answer to part 2? In part 2, I happen to do a timer here because, as I said, the first solution took a while. My first implementation of part 2 took a while. But how does the parsing look like? Well, maybe we can step through it, starting with the main parse function. So when I'm calling parse on the almanac, what does it look like? First of all, I'm just skipping I'm skipping the seeds using this tag thing. And then the seeds are just a separated list of digits, separated by space, right? And then I just turn those into integers. So that is this part right here. And then I skip this extra new line. So now, how do I do the rest of it? Well, in nom, I can just break these up into chunks, right? Notably, they're separated by double new lines. So I can create a separated list by double new lines. And then just for each of those, so for each of these, how do I then parse that? Well, I call the parse mappings. And that's this right here, right? So this first part just essentially ignores this first line right here. Turns out it's not really interested because you're just mapping from one to the next, and it happens to go from seed to soil, soil to fertilizer. It happens to go in order, right? So you do this mapping first and this mapping. So how do you do that? Well, now after I've gotten rid of that first thing, I just need to apply these I just need to get each of these mappings, which are just 3 numbers, in a separated list by new line, right? For part 2, I should say that I had to sort it, and so if you think about, you have these two mappings in a mapping group, I guess I should call them. The way that it works is, for part 2, it was helpful to have these sorted. So instead of 50 and 98, instead of this way, I would have 50 first and 98. But anyway, that's for part 2. Having those sorted is helpful. But anyway, you separated by new line, I do a mapping parse to get these 3 values. So what does that mapping structure look like in the parse? Well, the parse is actually not hard, right? It's just destination space, source space, length. Those are the 3 values. That's the way they describe it. They describe it better than I could, but considering, like when they say consider this example, you have a destination range, a source range, and the length of the both, right? So what is that saying? It's saying like 98 maps to 50, 99 maps to 51, and that's it for here. There's only 2. Here there's 48, saying 50 maps to 52 and up to whatever 99 corresponds to 51. And so on and so forth, right? There's some into it in that in this mapping right here, right? I may not have said that right, but the idea again is you have some destination, some source, and some length for both of those, and you're supposed to find the seed. Like, can you find the seed within all of your mappings? And if you find it with one of them, you apply it, and then you can move on to the next mapping at the next depth. If you don't find it, then in any of the lists, then it's just the same number, right? So 10 is not in any of these groups. So 10 just falls through to the next mapping as 10, right? So again, how do you parse that? The way that I just went a digit, a space, a digit, a space, and a digit, and then I can parse those and create a new one. The way that I described the mapping was actually a range and a delta, right? So if I think about what is my source range, like 98 to 99 or whatever, or 50 to 100, and then what delta should I apply to the number if I'm in that range, right? The idea being I don't want to keep a list of all the numbers. I can just keep like the start and end and what delta to apply to those values. So I have the source and plus the source length, and then the delta is the destination minus the source, right? The difference between the destination and the source. Given that, I can actually iterate through them pretty easy. I can do some calculations pretty easy. I can say if I want to know if a value is contained in this mapping, I can just ask the range, right? Rust has a range structure. I can just say, hey, is that range within these? Is that value within this range? Is it contained in it? And then if I want to apply a value to this mapping, I just add the delta to that value, right? Those are pretty easy functions to do to the mapping. If you're not familiar with the range operator, it's right here. There's just really a start and an end index. It says it is inclusive for the start and exclusive for the end. So in this case, that was okay because when you're doing additive stuff, you obviously don't include the last one, right? I actually have a funny story about this with my family that I'll have to tell sometime, where we had a big argument about pick a number between 1 and 10, whether or not it was inclusive or exclusive. Well, Rust is very explicit, so we don't have to get into an argument about it. It is inclusive for the start, but not for the end. Okay, so how do you solve part 1 then? Right? Remember, essentially what you're going to do is you're going to take this seed number and you're going to say, hey, is it within this range? If it is, you apply it. If it's not, you try this one. After you've gone through all of them, if it doesn't apply, it's just the same number, and then you do it to this group of mappings. Then you do it to this group, and you do it so on and so forth until you get to the end and you get a number. That's actually not hard, so I think I have an apply seed function to do that. If you think about what this is doing, it's just saying for each of the mappings, I'm going to try and find each of the mapping groups. I'm going to look at each of the mappings and see if it's contained in that. If it is, I'm going to apply that value, and then I can move on to the next mapping. At the end of all of that, I've gone through all of them, and I can get a value back. So what does the solution to part 1 look like? Well, it's actually relatively simple. I just can go through all the seeds, and I can call apply seed on each of those numbers, and then ask what is the minimum of all of those values, right? So I can iteratively go through them, keep track of the last one, or the smallest one, and pick that smallest one. Not too difficult. And it turned out I don't think anyone had a problem with that. It wasn't very difficult. So there's a lot of it talking about how to do that, but you come up with this solution. Notably, these are large values, right? Turned out not to be a big deal for part 1. It is a big deal for part 2, right? In part 1, if you think about it, as you're like, oh, I only have a dozen seeds, and I'm really only looking for is the number within this range, right? And if it is within that range, then I can just add the delta. So the calculations aren't really dependent on the size. You can really use any numbers, and there's a very like n number of calculations you have to perform for each seed to get to the solution. It's not like a difficult algorithm. What changes in day 2 is they say, hey, you know how you had this list of seeds? So instead of having 4 seeds, you actually have ranges of seeds where 79 and 14 are a pair. And what that means is calculate all the seed ranges from 79 to 93, exclusive of 93, right? So 79 to 92. And from 55 to 55 to 67 in this group right here. So now instead of having 4 seeds, you have 27 seeds that you have to calculate. For these two, that is not a big deal. For your actual input solution, that is a big deal, right? If you think about this range right here is 109 million. This range is 86 million. This range is 205 million. So you're very likely now calculating billions of seeds as opposed to dozens or hundreds of seeds. And that does have an effect on your code. Let me show you what my initial solution was. I thought, I wasn't really paying attention to the sizes. I thought, those are big numbers. Maybe they're not super big though. Can I just use something like rayon to parallelize it? And that's where my graph ended up looking like, let me pull it up again. My computer started looking like this, right? Where it's saturating all the CPUs and it takes 94 seconds to solve it, right? Rayon is actually a cool tool though. I will say that if you want to do parallel processing over lists and over iterators, it's a cool way to do it because it's kind of magic is you just say, hey, instead of doing into iter, I want to do into par iter, meaning do this in parallel. And now it will call your apply function on all of the numbers that produce out of this, hundreds of millions. It will do it in parallel on all the CPUs you have using as much, as you're able to. This took, though, 94 seconds to run, and I don't know what's wrong, but it actually was off by 1. It didn't give me the right answer at first, so it gave me this number for part 2, but 85 instead of 84. And I don't know why that was wrong, but it was wrong. And I did not want to, first of all, I didn't want to say like, do I just want to keep trying to solve this problem and have it take 94 seconds each time I test it? Because the test code, the test input runs really fast and I got the right solution to it. I don't get it though when I do this. So I had to think about it a lot more. And I just want to walk through that process a little bit of how I came up with the solution. The way that I started thinking about it, what my first thought was, okay, well, if I can't apply it to a single seed iteratively in a list, is there some way for me to apply it to a whole seed group? And that's what made me think about it, right? So if you have that range of, I don't remember the numbers, 79 to 85 or whatever, right? This is your seed group right here. How would I apply a mapping to that whole group? And it turns out, if you think about it long enough, you come up with the realization that there's really only a few ways that you would apply this. So assume you have a seed group starting at seed 0 and seed n. You ask yourself the question, what happens or how might a mapping apply to this seed group? And the first is, well, what if the mapping encompasses the whole seed group? Well, that's super easy. You don't have to call apply on all of them. You can just call apply on seed 0 and apply on seed n. And that is your new seed group, right? It's completely encompassed, so you can just call the apply function there, and that solves this one. That's a pretty simple case. The other cases are where there's some kind of overlap, right? So imagine your mapping is now here and here. You now have this position here where you say, oh, there's some part of it that's within the mapping, right? And then there's some part of it that's not within the mapping. So you can call apply. Oh, that's a terrible little squiggly thing. But you can call apply on this function, and then you need to like break it up, and you need to, you can call apply on this function, and now you need to break the seed group up and say, okay, I have a new seed group right here from S0 to the mapping's 0th element, and I now need to do now I need to find a grouping that fits there, right? The same thing applies on the opposite side, right? So imagine the mapping is now this way. It's just different numbers, right? This part you can apply, and this part is, and this part right here, you create a new mapping, a new seed group for, this one is mapping end and seed n, right? Sorry, this is a little, but I hope you get the idea. Is there's some group of them. The quote unquote worst part is, what if the mapping is only this big? Well, now you need to break your seed group up into 3 pieces, right? So this part you can do the apply, and then you get 2 new seed groups right here that you need to process, right? And so I went through this process, and it turned out that it lended itself to a recursive solution. But I want you to, when I walk through it and solve it, I want you to know that I didn't get there at first, right? It took me a while to like apply all these things. So even though you didn't see me thinking through it, I don't want you to get some impression that I just knew this thing outright and I was able to solve it recursively. Some of these recursive algorithms take time to fix. But again, this is the key to the solution, right? Is essentially for each mapping, you can kind of do this, and you're going to have some parts you're going to be able to apply, some parts you're not going to be able to apply. Or in the one case is if you're outside of all the mappings. Remember, I sorted it, so there's always this range of mappings where it will fall somewhere in, but then there's areas where it won't fall in either. And if that's the case, then now you know that you can't do that you can just fall through, I guess is the way to think about it. And so you take this and you just kind of do that recursively to get to your solution. So what does that look like? I'm breaking it into chunks, and then I'm calling this helper function where I start with the beginning and the end of my seed group, and I start at depth 0. This is where the recursion is helpful. If you think about the depths of the mappings, as you're breaking it up, you get pieces that you can further, that can go to the next level, but pieces that can't and you need to do more work on. So the recursion includes the ranges and the depth. But this helper function is essentially saying, starting at this position and ending at this position, give me the minimum value when I recurse all the way through at all the depths. So what are the base cases here? Like, that's what I always think about when I'm starting an algorithm, a recursive algorithm. The first is, well, what if I'm at the end of my depth, right? If I've gone through all the mappings, now I'm done. I can't do any more mappings with that range. So I'm just going to return the minimum of my seed group, which happens to be the start value, right? The start will always be the minimum. This case right here is the case where we say, well, what if my whole seed group is below the first mapping? The whole seed group, the start and the end are below there. In that case, I can just go to the next depth, right? So if I'm below there, I just go to the next depth. I go to the next depth and I can check it. Then I can loop through all the mappings and try and find which of these apply to my situation. Am I somewhat, do I have some inside of it, some outside? and eventually you're going to iterate through all the mappings and find some place where you apply to some and not others. And that's just what these blocks are, right? So if my start is less than the range, I know that I have some piece at the beginning of the seed group that doesn't apply, but I have some part of it that may apply, and I can check that. I can check that later, right? So that's what this is saying. If I'm somewhere in, if my start is somewhere in there, but my or is not in there, but my end probably is because of this check right here, I can then break it into two pieces and then just do it and call the helper function, right? So I know the beginning of it, the start range, the start of it, the first part of it, I can just pass on to the next depth. The second one, I need to check again for my depth. I need to check again at this depth because I don't know if the end is within my range or within the mapping, or it goes past the mapping. I now know that this new chunk that I've created, it definitely starts at the beginning of the mapping, but I don't know how far the end goes, so I'm just going to recursively try again, and it will fall through that helper function when I do it again at this depth. It should fall through to either this one or this one right here, right? And do that. Okay, so now I've dealt with my start. Now the question is, at this point, are both start and end within the range of the mapping? And if it is, then I just apply to both, right? That's this case right here. If the start and end are there, then I can just apply to both. Now I can ask myself, well, if the start is there, but the end is not because we already checked it here, now I can apply from the start to the end of the range. That's these type of things right here, right? I can do an apply on a piece of it, but now I need to do the rest at this same depth. This is the kind of the same as this right here. Now, the other thing to point out is I can actually ask what the minimum is at this point and return that value. Why is that? Because I know I'm doing this recursively, right? I know that the minimum value here will bubble up, and so that's the key to simplifying the algorithm, I think, too. Is when I was first trying to solve it, I was like, oh, do I keep a list of these mappings? But I kept having issues where it would overlap, or where one seed group would turn into a million seed groups as you were iterating through the depths of the mappings. And understanding that, hey, from this point, once I do apply here and I call the function here, having that minimum value helps me solve it, right? Okay, one last case. After we've gone through all the mappings, if none of these have applied to it, I know that I've gone over all the mappings, and that is the same as the very first case we tested here, just on the opposite end of the group, where now I know it doesn't apply to any of them, so I can just go to the next depth. And again, all I'm doing is I'm saying I'm going to apply this thing. I may break up seed groups, but I'm basically going to do this thing over and over again and just find the minimum of all those groups as I'm doing that, and that will help me solve the problem. Okay, so it actually turns out not to be a lot of code. Like if you look at this and remove all the comments, it's not too hard, but it did take me a while to get there. So I just want to reiterate that is when you're trying to solve these problems or any problem in general, don't feel bad if you struggle, right? The key was me thinking about was, what if instead of applying one seed at a time, I apply it to an entire seed group, right? And then I could say, how does that look in these things? How does that look with those mappings? And then how can I do that recursively? And then that helped me get to the solution. So here's the answer. How does that's what the answer produces, at least for my input. And how long did it take? 0 milliseconds, some number of nanoseconds. I don't know why I just did the elapsed time thing, and that's what it returned. Oh, I did it as milliseconds, so that's why. Excuse me. But again, much better than the 94 seconds and trying to heat up my office with my CPU. A much better solution to day five, I think. So there I am. That was my day five solution. Again, that you're looking at it, it's day six. I only had time to do this in Rust. I hope I'll have time to come back and do this in Haskell. I don't feel like this was particularly hard. The parsec parsing shouldn't be too difficult. Part one should be relatively easy. Again, if you look at like part one, this is very like functional in nature. Part two, I don't think is much more difficult. Again, this is just you're taking ranges and trying to split them up and put them back together. It would be interesting. I'll keep trying it in Haskell. We'll see how far we get. But I would love to see your input and solutions. For day six, I'm hoping I actually have time to go live and you can see me try and do day six and see me struggle through the answers and stuff like that. But I hope you guys enjoyed it and always want to hear your input. And we'll talk to you later.